Hello, hello. All right, so let's get started. I want to give this presentation and tell you a new perspective on how to build foundation models. And I want to talk to you about this new perspective's impact in the society. And at the same time, at the very end, I'm going to leave you with one open problem that everybody is trying to solve right now, and hopefully open up some light for you to really think about, like where do you go from here? So early on, when we saw the results of pre-training foundation models, like from the OpenAIs of the world and DeepMinds of the world, one objective, foundation model companies emerged with one objective of intelligence at all costs. So maximizing intelligence along one axis to really get to the most kind of intelligent systems that we can get. Like the marketing term for it is AGI. This is where everybody wanted to get. But along the way, recently we have seen that this maximizing intelligence at all costs is coming with a certain type of challenges. And those challenges are basically the limitations that we have around compute, chips, and the market that we are seeing right now. Memory prices are actually going up, and you're getting limited on how to deploy these solutions like at scale. You're seeing that efficiency as an afterthought is not a solution. You cannot just rely on scaling AI systems and then have, let's say, post hoc quantization kind of methods to actually optimize your solutions. You have to think about efficiency from scratch when you design AIs. And you've seen recently that there are governance, compliance, and safety on distribution of intelligence that actually is a blocker on actually taking AIs to the next step. You have also seen that the open source AIs are getting a lot more powerful. Like for a foundation model company, it is something for them to think about. So distribution through open source itself is also another challenge that we need to think about. So to solve this, we thought about a new framework. We thought about a 3-axis problem on building foundation models. And how do you do that? Not just having like intelligence maximization, but when you design foundation models from scratch, think about intelligence from the pure capability point of view, but also think about efficiency of this computation from scratch in terms of computational cost of intelligence. For example, we have the transformer architecture powering all the AIs of today. We can also change that. We can start thinking about innovations across architecture to getting more efficient realization of intelligence. And at the same time, think about where this intelligent system is going to be hosted, in the physical world. Because right now, all the solutions that are like foundation model companies are focused on have been like dominated in the data centers. But there is actually an abundance of resources outside of data centers in the physical world as well. So if we have an objective function that can allow us to build efficient general purpose AIs at every scale, this is basically the new framework that we build liquid AI on top of. So we are a foundation model company that actually works across optimization of these 3 axes. How does it look like in practice? The way we design AI, we put matters of, let's say, foundation model development across architecture, learning algorithms, data efforts, all of this stack. And we basically loop that with the physical world. When I say physical world, it starts from chips, from systems like mobile phones and laptops that you communicate with the physical world through them, and to, let's say, devices like robots, cars, and anything else that moves in our society. And we co-build an optimization loop between the substrate, which I call like those kind of devices, and the innovations that we have on the research side, doing this with a meta AI algorithm. So at the company itself, we built a meta AI system. This AI system is actually like a search-based algorithm that at the same time, across the 3 axes that I actually introduced for you, it actually optimizes through those axes. Minimum amount of memory. Imagine given a processor on top of which you want to deploy the AI. Minimize the amount of error while minimizing memory usage, while enhancing kind of the speed of the models as an optimization problem. This is basically AI's designing AI, so that's kind of the framework that about 3.5 years ago, like spun out of MIT, we have started like developing. So the core technology at my company is all about basically building optimization platforms across 3 different axes: substrate, intelligence, and efficiency. These are kind of the 3 places where we go. I also put like a research paper here for you to have like a look at, like from 2024, to really see how we are thinking about this automated foundation model design as a whole. Now, let's talk about the impact of these systems. As a result of our automation foundation modeling platform, we are getting into something that we call liquid foundation models. These are a new class of artificial intelligence systems that are very lightweight, and they can fit even on a Raspberry Pi. So you can host these models on the smallest unit of compute and larger. The systems are actually extremely popular. These models has been downloaded with a rate of over 1 million downloads per week. So we are like, from the US side, we are actually like probably from the open weight lab in the top 10 kind of companies that are actually releasing open source models. And we have done that with an amazing amount of efficiencies. Now, let's look at some stats. When you optimize foundation models from scratch with the goal of 3 things, as I mentioned: memory, latency, and quality at the same time, you can unlock new Pareto frontiers. Here, what you see is a comparison of a bunch of models across quality on the y-axis, and on the x-axis, you see the decode speed, or the speed of computation. The speed should be higher, and the quality should also be higher. You can see a comparison between like how these models are actually performing. At the same time, this is another graph, very similar thing, that on the x-axis, you see quality. On the y-axis, you see memory. The lower memory footprint is better. So we have a range of models ranging from like 100 million parameter models to, let's say, 100 billion parameter models. So far, we have actually released some of these models in an open weight fashion. And this is a report from Artificial Analysis that you can actually see the fastest models on the planet right now. There's a Mercury 2, and there's a liquid foundation model, LFM2, on the second instance. And from the price point of view, this is kind of the cheapest foundation model that you can actually get. The reason why we can actually unlock such efficiencies is because of the 3-axis kind of perspective that we have. Maximize intelligence while having a look into efficiency of models, and at the same time caring about where intelligence is going to go. Now let's get out of this benchmarking kind of situation and talk about markets. When you have models that can be running on any kind of silicon, like on CPUs, GPUs, or neural processing units, you would be able to host them on devices. So you can go into automotive business, you can go into mobile, you can go into laptops, you can go into wearables, you can deploy models and intelligence across many, many different pipelines. And there is a lot of processors in the world. In fact, there are like 2 billion processors every year getting constructed outside of data centers that you can put intelligence on top of. And we are actually like enabling intelligence on top of those surfaces. The value of having fast models that are designed for smaller processors, is the fact that you can also run them in the cloud. The more compute you give them, the faster operation and the lower latency kind of profile you get. So you can also like host them in constrained environments when you do not have access to massive or abundance of compute. For example, in the automotive business, which is one of the verticals that we work with, we are on the path that by 2028 be on 50 million cars, enabling basically in-car intelligence. The thing that you know, like imagine an interface where you have your car is actually one of those private spaces where you can communicate with your car and control your car completely with your voice, and also like with let's say sensor kind of infrastructure that allows you to really have full-blown experience of an intelligent system. We are actually hitting on a laptop 1,400 tokens per second as a web browser. So you can actually put our technology, this is actually a Hugging Face demo, that you can actually try it out. It's called Web GPU. You can try it out, and you can actually get it on your laptop up to like 1,400 tokens per second, systems that can actually solve problems and call tools for you. You can build agentic AI on a laptop with this kind of speed. We just recently, Shopify is one of our clients, and we just recently hit 1 billion requests going through Liquid Foundation models across the Shop app. If you go to the Shop app in Shopify, you can actually, like whatever you type in there, it goes through a Liquid Foundation model. With AMD, we have been like democratizing access to local intelligence. For example, we're building specialized AI systems like, let's say, a summarizer that is really, a document summarizer that is extremely good, and it only consumes about 800 megabytes of RAM on a laptop, and it can perform as good as Claude Sonnet, like the best version of the Claude Sonnet. So we are talking about maximizing capabilities of specialized models without burning out, like basically on compute and cost. And then there was a video here to show that you can also get these systems power robots. For example, we had skill selection layer for robotics. Like that's something that we can enable, like on top of models, because the models that we are putting out there, they are multimodal. They can process audio, vision, text, and other formats of signal. So, as I told you, as Liquid AI, we are optimizing this perspective of before design of a foundation model, you're maximizing for efficiency, and you're maximizing for intelligence while having efficiencies in mind, you know, cost efficiency, compute efficiencies, and at the same time, the substrate where intelligence can go, and design that as an AI, designing AI problem. Basically a recursive kind of self-improvement kind of loop. And we've designed something like that to really build an adaptive layer on top of the silicon that is outside of data centers. This way, we can actually bring intelligence to everybody. Now, I want to conclude my talk by giving you a question to think about. You know, we have been known as Liquid AI as guys that we have been like innovating across architecture of intelligence. We have not been building transformer-based architectures. We have been researching decade-long how can we learn inspiration from brains to really bring these inspirations back to machine learning. Because your brain is consuming, it's a general purpose AI, your brain, and it consumes 20 watts of power. So if you can actually learn from there are like a lot to actually unlock. So think about like where we are. There is an interaction when we design these highly powerful AI systems. There are matters of architecture innovations, learning algorithms innovation, and data effort innovation in place. A combination of all of these things is going to give rise to, you know, like the most efficient way. So far, we have seen only scaling a certain type of this architecture, certain type of learning algorithm, and certain data efforts giving rise to basically where we are today with the highest kind of levels of foundation models. But there is a zoo of opportunities to really explore across this tree, and it's not only the architecture that has to be explored. I strongly believe through evolution, intelligence emerged as a social experience. So think about it like this. Intelligent behavior, it's an emergent phenomenon. Nature actually gave rise to intelligence being because of like maximizing survival capacity. AI's foundation models of today are systems that are, what we did, we tried to actually build a process called next token prediction as a learning algorithm. And that next token prediction gave us a capability or an emergent capability in AI models or in neural networks called in-context learning. In-context learning was emerged from scaling next token prediction as an algorithm. So we started from next token prediction, we ended up with where we are today. And this in-context learning implements a pseudo gradient descent, pseudo optimizer, so it's getting very technical. But what I want to mention is that there was a prior that gave us to the emergent properties of learning systems. As I mentioned, human brain has a massive capabilities of different types of learning. For example, you can learn from examples. You can learn in short period of time and in long form of time. You can actually listen to something and at the same time speak and at the same time adapt. There are massive types of neural architectures that are happening in your brain that are giving rise to intelligent behavior. So that many mechanisms of learning are emergent properties of natural evolution. This is actually what happened. Now the fundamental question that we have to ask is this. What should we start with from which we can emerge multiple kind of learning schemes? What is that algorithm that we have to start with to really get to the place where you have multiple learning algorithms emerge? Because if you start mimicking reinforcement learning, like with the reinforcement learning pipeline or mimicking behavior, it's just going to give you a mimicry machine. They're going to be capable, but they're not going to give you the maximized, basically, intelligence at all costs. They're going to give you maximized intelligence at all costs. They're not going to give you an efficient form of intelligence that is basically, we're talking like powerful AI. What we want to get at is to really deeply think about what kind of priors we can start a learning process and what combination of these tools that we are seeing across architecture, across learning algorithms and data efforts would give rise to that format of intelligence. Okay, and my goal is to give you that question and really justify it through that perspective of really, there is a big open question still. How can we build something that is actually as efficient as your human brain and being able to perform multiple mechanisms of learning and actually exhibit behavior like humans? Thank you.